Hello and welcome to the A-Town Notes January lecture series for 2024 for Mathematics Extension 1. My name is Ryan Simon and I will be presenting today's lecture for you guys. So yeah, let's get started. So Haranish is the one that's put together these great slides for you guys, and here's a bit about him. So yeah, have a quick read of that. And in terms of a bit about me, I did Mathematics Extension 1 and 2, Physics, Chemistry, English Advanced, and I also did Design and Technology. I graduated in 2022, and I'm currently doing Civil Engineering and Physics at UNSW. So yeah, that's a bit about me, so let's jump into the content. But before we do that, let's look at some quick tips. These are very general math-related tips, but they're also applicable to quite a range of sort of STEM subjects. So yeah, here we go. Anyone can be good at math. Some people simply require more practice than others. However, if you work hard, you will succeed. So yeah, put in the time, put in the effort, put in the practice, and you'll see results. Here's something that I always talk about: enjoying the content. Enjoying the content is sort of a very big part for me in this subject, because if you actually ever sit down and look at these topics, you'll see that they're actually quite interesting in themselves, and they're actually quite powerful in a whole range of applications in the real world. Not only that, they're interesting in themselves. And also in terms of like exam preparation, that sort of thing, I recommend using past papers. And I'm sure you would have heard that like a million times already. But towards the exam period is probably when you would be doing timed exam papers under exam conditions, that sort of thing. But although it's quite early on, you guys can still go through exam papers, particularly older ones. Maybe save the more recent ones for time practice, but go through older ones, do questions for topics that you've already done, or topics that you think you're comfortable with. Do those questions, start observing the sort of style of question that they like to use, and yeah, get comfortable with sort of the HSC layout and that sort of thing. Exam technique is also very important. It's very much dependent on each individual person. So yeah, start experimenting with different exam techniques, and see which one works best for you. Maybe you have to take some recommended advice and adapt it. Maybe you have to sort of go through the easy ones, come back, or different people have different exam techniques. Sort of go through and experiment with different ones, particularly early on. Now that you guys have sort of a good degree of time before your actual exams. So yeah, exam technique, and then in general, again, feel free to ask any questions about anything related to high school and maths, and that's what the slide is for. So yeah, let's get started. In terms of what today's schedules will look like, we'll be covering two sort of main topics. One is vectors and one is calculus. So here's sort of a brief overview of the vectors topic. We'll be looking at what a vector is, vector notation, vector operations, vectors in component form and that sort of thing. And then we're going to jump into some integration, not too much, not too complicated, not too many application-based questions, just sort of basic integration. And yeah, we'll see how that does for time, but let's jump into some vectors. So yeah, if you guys have seen the syllabus, this is what it looks like, and these are the two topics that we'll be covering. Again, these are very sort of brief crash courses into the topics. There is a lot more to these topics, but these sort of foundational skills will set you up for further exploration and further study of these topics. So yeah, vectors. Now, vectors is a new syllabus topic, so just be careful about that. And as you guys would have already known, the syllabus for Mathematics Extension 1 was changed in 2020. This is actually a question from the 2020 HSC paper, multiple choice question 6, which used the vectors topic. So yeah, what does that mean for you guys? Well, that means that you guys are the fourth cohort to do it for the HSC. And so you guys only have 3 official HSC past papers at your disposal, which covers this topic. But you guys also do have access to a range of resources for practice for vectors, including textbooks, trial papers, and sample papers which NESA has released. Highly recommend using them. You can probably find most of these, like the trial papers and sample papers, on the internet. Textbooks questions as well. Some students, for some reason, tend to avoid textbook questions. Now, I don't recommend doing every single textbook question, because, like, even the easy ones, but go through and find what the ones that you think would be challenging, and do those ones, because those are also extremely useful resources. So yeah, use as many resources as you can, because in terms of past HSC papers, you only have 3 which cover this specific topic. So, physics students may find concepts of this topic easier to grasp, mainly because vectors is used a lot in physics. And I believe in preliminary physics, you would have started off looking at some vectors and sort of looking at magnitude and direction and all that sort of stuff. That's because the whole vectors concept is extremely useful in physics and is very commonly applied to like pretty much almost everywhere in physics. So yeah, vectors. If you guys have done physics, it may be a bit easier to grasp when it comes to this topic in Mathematics Extension 1. Mathematics Extension 2 students who have covered the complex numbers topic may also find this particular topic easier because complex numbers is sort of an application of vectors with some extra stuff added, but vectors in itself is much more broad. So yeah. But for those of you who don't study these subjects, don't worry. As long as you approach it with an open mind and are willing to put in the time and effort, you too can succeed. So yeah. And again, vectors in itself isn't too complicated of a topic, it's particularly in this form where we're dealing with two dimensions and we're dealing with sort of very concrete examples. It's very much not a difficult topic. It's just something that you need to practice, get used to the notation, get used to sort of the um, ways of manipulating it, and then start applying it to different situations. So today we'll be covering the foundational material for the vectors topic, like I said, and harder concepts in the syllabus such as dot products and vector projections will be saved for another time. So yeah, those topics again use the same concepts that we're going to talk about today, but we'll be going through them maybe at a later time, or you guys will cover them at school. So it's okay to be confused, especially if you are learning these ideas for the very first time. Don't be afraid to ask any questions at any time. That's why the slider is there. Feel free to ask any questions, and I'll try my best to get back to answering you as quick as possible. Um, it's okay to be confused in the sense that if you guys are seeing this topic for the very first time, this is meant to be sort of more of a crash course sort of style of things, rather than a complete, something that you guys would have done over maybe 3 or 4 weeks is not something that we can do in 2 hours, completely condensed, completely exhaustive. But if you guys see it here, have a think about it, maybe do some practice, and then you guys see it again at school and then do more practice, it's going to be so much easier, so much more clear, and you guys can deal with more complex situations or complex setups. So yeah. Okay. So what? Let's start with defining a vector. What exactly is a vector? Well, a vector is a quantity that has both a magnitude and a direction. Now, this is in contrast to a scalar, which is a quantity that only has magnitude. Now, these are best expressed with examples. I think it's good to define these two words as well, magnitude and direction. Magnitude talks about how big something is. So if we were talking about, so a very common example would be velocity. When we're talking about velocity, that's a vector, and it's got a magnitude, as in, we could say 30 kilometers per hour, or 10 meters per second, or 3 meters per second, or whatnot. That's the magnitude, how big it is, and then we can give it a direction. We can we can provide information about which way the velocity vector is pointed, which way the person's running, or which way the car is traveling. So you could say 20 kilometers per hour north, or 30 meters per second south, something like that. That's what that's an example of a vector. But in the case of a scalar, that's a quantity that only has magnitude. So a very common example of a scalar would be something like temperature. So when we're talking about temperature, I could measure the temperature outside, and then let's just say it's 24 degrees Celsius, right? Then that would mean it has a magnitude, but it's not. You can't really give a direction to a temperature, can you? So that's why it's considered a scale. So the magnitude would be 24 degrees Celsius. It doesn't have a direction, so it's a scalar. So here's some examples, and I'll give you maybe a minute or so to have a look at the slider. Sort of list which ones are scalars, which ones are vectors on Slido. And yeah, you would have already come across the majority of these ones if you do physics, but we'll go through them in just a minute. So I'll give you a minute to do that. And just for the interest of time, maybe a minute seems a bit long. Maybe we'll chop it down to maybe another 10 seconds. So yeah, remember vectors have magnitude and direction, whereas scalars have only a magnitude. And you sort of have to be careful with some of these terminology. We're talking about sort of a physics definition of these concepts rather than sort of day-to-day explanation. So just be careful about that, and I'll talk about exactly what I mean in a second. Okay, I think we can go through the answers. Firstly, um, yeah, distance is a scalar. So when we're talking about distance between 2 points or distance between 2 points on a map or something, we could say 15 kilometers. We don't when we talk about the word distance, um, we don't really talk about the direction, especially when we're talking about it in a physics context or a physics-based definition. But when we talk about the displacement of an object, we can talk about how far it's gone. Sorry, how far it's gone. So 15 kilometers, and we also give it a direction. So maybe 15 kilometers north. So yeah, there's a difference between distance and displacement, especially when we're talking about a physics sort of perspective. Um, so just be careful with that. Again, for something very similar for speed and velocity, speed is a scalar. So yeah, again, you could say 22 kilometers per hour, but velocity is a vector because it's also got to be associated with a direction. So you can say 22 kilometers per hour east. So it's speed, but with a direction, um, in a simplified sense. Technically, there are more differences to it, but in a simplified sense, I guess you could think of it as speed with a direction. Um, but yeah, make sure you're careful about talking about speed as a scalar and velocity as a vector. Temperature is an example that we talked about before. It is a scalar because it has no direction. You can't really associate a direction to temperature. Um, Mass is a scalar, but weight is a vector. Now, that may seem a bit confusing if you guys don't do physics, but weight talks about the force of gravity on an object, right? Whereas mass is a measure of how much, I guess, stuff there is. Um, so that's mass is what you measure in kilograms. Weight is what you measure in newtons. But because weight is a force, technically, the force vector also has a direction. So forces are always vectors, and so it also has a direction, whereas mass is just a scalar. So you could say 10 kilograms would be the mass, the weight would be about 100 newtons downwards or towards the center of the earth, because that's the direction of gravitational force. Now, there are many ways we can notate and represent vectors, and different sort of authors like using different notations. So just be aware of the different types that may turn up, just so you're not sort of caught off guard. So for example, vector quantity may be represented geometrically as a directed line segment, algebraically as a pair of components. Now, that's sort of the representation of them, but there's different notations as well. We'll talk about that in a second. We'll talk about that soon, but first, let's look at the geometric form of a vector. Firstly, a vector can be represented as a directed line segment. What does this mean? Well, it means that a vector can be represented as a line from A to B with an arrowhead indicating its direction and its length indicating its magnitude. So if I was to draw that, turn on the pen, we could have point A here, point B here, and if we have an arrow that joins those 2 points, the distance here, or the length of this vector, gives us information about the magnitude, and the direction of the arrowhead gives us information about the actual direction of the vector. So in that arrow, or in that sort of drawing, you've sort of encoded both the magnitude and the direction. So therefore, we can talk about a vector from A to B, or vector AB is usually the way it's written, and you'll see it written like this with a little line on top, or an arrow on top, to show that it's a line, or show that it's a vector AB. So the end with an arrow is called the head. So that's the head. And the end without one is called the tail. Pretty sort of common sense terminology. A is the tail and B is the head for this particular vector. Yeah, so it's already been drawn. Now we can notate this as AB, like I said. Yeah, we can notate this as AB, like I mentioned. And you can also notate it with a bold lowercase letter like this, A. And we can also notate it with a little tilde underneath it, like this. A with a little sort of curly thing underneath it. That all three of these mean the same thing. They all denote a vector, which in the lower two cases you're calling it A. In the upper case, or in the first case, you're calling it AB. but they all talk about the same thing. So yeah, that's a vector AB. And since you'll be handwriting for the HSC, A, B, and A will be more appropriate to use. So you can't really sort of bold write things. I mean, you can, but it's not really a good use of your time, and it's probably not going to turn out as neat. So rather than using the bold, the two most common handwritten notation that you'll see is A with a little tilde underneath it and AB with an arrow on top. Both of them talking about how it's a vector. Now, the key thing here is differentiating between a vector and a scalar. Many times with scalars, you'll see just, for example, the difference between A and A tilde is that A is just a scalar, it's just a magnitude, whereas A tilde is a vector. It's got a magnitude and a direction. So it's very important to differentiate between those two quantities. Now, the magnitude of a vector is notated using two straight lines surrounding an expression like this, AB, or A like this. You probably know this as an absolute value sign, or 4-unit students may know this as the modulus notation for a complex number. In this topic, this particular notation refers to the magnitude of a vector, which is the measure of its length. The magnitude of a vector is a scalar quantity. So if we're talking about a vector, AB, so A and then B, the actual length of this vector, or the actual magnitude of this vector, is denoted by this notation here. Or if we're calling this vector A, it's also equal to A. So for example, if we're talking about a velocity vector, then that is the actual 30 kilometers per hour. So for example, that could be, or if we're talking about a displacement vector, maybe it's 30 meters, right? Or 25 kilometers per hour is the magnitude of that velocity vector, and so on. So yeah, don't confuse this with an absolute value sign, so you have to make sure that it is actually a vector in here, and it's not just a scalar. If it's a scalar, then you're just going to take the absolute value of that, but make sure you differentiate between absolute value and sort of the magnitude of a vector, or the length of the vector. And yeah, 4-unit students may know this as the modulus. It's very similar, very related, because if you treat complex numbers like vectors, then the modulus of that vector is sort of the same as the magnitude. Sorry, the modulus of that complex number is pretty much the same as the magnitude of the vector. You could think of it like that, but yeah, just be careful with the notation. All vectors can be uniquely identified by its length, magnitude, and its angle it makes with the horizontal or the direction. So you can uniquely identify a vector by looking at the magnitude and the direction. And it doesn't matter where you move it, as long as the directed line segment is the same length and pointing in the same direction, it will represent the exact same vector. So if the vector A is represented by this directed line segment, then it will also be represented by these ones as well. These ones, so this and this, or this, or this, or this, or whatever, wherever you put it, as long as this length and the direction stays the same, it's still vector A. So this one's still vector A, this one's still vector A, this one's still vector A, and so on. Because the magnitude has not changed and the direction has not changed, it is effectively the same vector. So if the vector A is represented by this directed line segment, if this is vector A, this is not equal to vector A, because clearly it has maybe it has the same length, but it has a different direction. So therefore it is not the same as vector A. This here, for example, may also have the same length, but it's not the same direction, so clearly it's not vector A. Similarly, this one, although it has the same direction, it's much smaller than vector A. It's much smaller than vector A. Therefore, it is also not vector A. So if you want two vectors to be identified as the same, they've got to have the same magnitude and they've got to have the same direction. So that's what I mean by uniquely identifiable. Now, an opposite vector is a vector with the same magnitude but in the opposite direction as another vector. So the opposite vector of A is negative A. So if A equals AB, then negative A equals BA. So here's vector A that we've been talking about all this time. That's AB, right? Oops, sorry. So that's vector A. And then here's vector negative A. And the only difference here is that it's faced in the opposite direction. So if vector AB is directed this way, vector BA or vector minus A is directed in the opposite direction, but parallel. So the magnitudes are the same, so the sort of direction is the same, but it's in the opposite face, but it's facing the opposite way. So two vectors are considered parallel if the lines of the directed intervals representing them are also parallel. That is, that they have the same slope. So parallel vectors can either be going in the same direction or going in the opposite direction. So if you have these two vectors, they're considered parallel because their directions are the same. If you have these two vectors, they're also considered parallel, although this one's pointing upwards and this one's pointing downwards. They're sort of gradient, I guess you could think of them. Think of it is like without ignoring the direction, but looking at sort of the gradient of those lines, I guess you could say, it's pretty much the same. So although this one's going upwards, this one's going downwards, they're both along the same direction, just in opposite ways, I guess you could say. But the way that sometimes you might hear this being termed anti-parallel. Effectively, they're still parallel, they're just in opposite directions. These two vectors, however, are not parallel because, firstly, they're completely. The reason is because they're in opposite directions. They're not in directly opposite directions, but the angle between them is not 0 or 180. So the unit vector of a vector is a vector with the same direction as that vector, but with a magnitude. So just introducing a definition here. So for example, here's the vector of A of magnitude 3 next to its unit vector. So all a unit vector means is that if we have this original vector, A, which has a magnitude of 3, then we can actually take this vector and shrink it down so that it's pointing in the same direction, but it's got 1/3 of that length. So it turns out to have a magnitude of 1. So that's what it means by a unit vector. Any vector that has a length of 1 is a unit vector, and if it's a unit vector of A, then it's in the same direction but of length 1. So yeah, introducing some terminology here. So we use a circumflex symbol, which is a little sort of upwards caret shape to notate the unit vector. So for example, the unit vector of A is notated as A hat, sometimes they call it. The formula to find this unit vector is this one here, and I'll explain exactly what that means. It means that if we have this vector A, this original vector here, and it's got some original magnitude A, right, or absolute value A, or length of A, we can actually take this vector A and scale it down by dividing the vector by the length of its vector. So we could have A, which is a unit vector, being equal to the original vector, right? And then scaling it down. So that doesn't actually change the direction. All it does is change the length. Scaling it down and gives us the unit vector. Because if the original vector has a length of 3 and we divide it by the magnitude of that vector, which is 3, then we're going to have a unit vector which is in the same direction but of length 1. So the unit vector might look something like this. A hat. Now, again, unit vectors have to have a length of 1 by definition. So this A hat here is a unit vector of A because it's got a length of 1 but it's in the same direction. And this is a sort of formula, I guess you could say, to find that unit vector. If the head and tail of a vector are in the same point, we get what is called the zero vector, i.e. the vector A to A. The zero vector will just be a singular point. Now, you just have to be careful here. There's a difference between just 0 and the zero vector. The zero vector is sort of from there to A to itself, for example, A. So vector AA is the zero vector, and it's notated like that, pretty much like that. The zero vector is different to 0 because 0 is just a scalar. Just the number 0 is a scalar, whereas the zero vector is a vector, and you have to be careful about the difference. Now, the zero vector has a magnitude of 0, clearly because it's going nowhere. If you want to get from point A to point A, how far do you have to travel? Well, zero distance, because it's not any further away from itself. And it's the only vector to not have a direction, because, again, zero vector doesn't really make sense to have a direction. Despite this, it is defined to be parallel to every other vector, just by definition, and sort of as a consequence of a range of other vector theorems. So the zero vector shouldn't really come up that often in a question, but it's still something interesting to know. Yeah. Now, how do we add vectors? Now, it turns out that we can add vectors and we can multiply these vectors by scalars. We'll come to the multiplying bit later, but we can add vectors and we can also subtract them, but subtracting is quite clearly related to addition. But the key thing here is that we can add vectors. So we can take one vector and we can add it to another vector, or add it to itself. So to add a vector, it means that we place them head to tail. Now this is very important for you guys to look at. Very important to not get confused with, because there are a couple of different ways you can think about addition of vectors, and if you mix them up, then it won't work. You want to try and make sure that it's clear. So head to tail is probably the one that I prefer, because it's very clear, and it's you can actually do subtraction and addition with this, as long as you're careful with the signs. But this is what I mean. So if we have the vector A, so the same vector that we saw before, and we have a different vector B, then vector A plus vector B looks something like this. So we put vector A down, we take this vector, we move it here, right? And we take vector B and we move it here, so it's tip of A to the tail of B. So head of A to tail of B, or so you could say tip to tail, or you could say head to tail. Head of A to the tail of B gives us this final vector here, starting at the end of A, all the way up to the head of B, gives us the vector A plus B. So tip to tail, so you take these vectors, place them tip to tail, and then you start at the very start point, and then you end at the very end tail point, very end head point, and that will give you your final sort of resultant vector, it's called. So for example, So for example, here's another vector here. So yeah, for example, maybe I'll do something. It might be a bit easier. So we have vector A, and we have a different vector here, maybe vector B. Now vectors, so we're interested in the vector A plus B. So to figure out what that looks like, what I'm going to do is I'm going to take this vector, right, put it down, the entire vector, including the head. Let's see if I can do this. Okay, maybe I'll draw it in. I'm going to take the entire vector, put in the head as well. And I'm going to take this entire vector as here, vector B. I'm going to move it over here. I'll move the label A plus B over. It's a little tilde. And so what that's going to do is we're going to be left with vector A here, which we've put at the bottom. And then we've gone tip to the tail of B. And so we complete this triangle by going from the start of A to the end of B, or the head of B. And that leaves us with the vector A plus B. So yeah, pretty easy here, especially the sort of the geometric interpretation is very simple. Tip to tail, line them all up, and then you complete that sort of shape by putting in your resultant vector, starting at the end of A, or starting at the tail of the first vector you put down, all the way up to the head of the final vector that you put down. That's that. Now, similar to addition with just regular numbers, vector addition is commutative. So that means it doesn't matter which order you add them in, you will get the same resultant vector. So what I mean by that is A plus B is the same as doing B plus A. Because if you have vector A, and then you put down vector B, right, we're going to get this green vector here, A plus B. Now, if we do B plus A, let's put down B first, and then let's put down A. So we're going to go B first, and then we're going to go A. That's going to give us the vector B plus A. But as you can see, just sort of visually from these two vectors, those two are effectively equivalent. So we can say that a plus b, adding the vectors a plus b, is the same as doing the vectors b plus a. So that means vector addition is commutative. Yeah, just geometrically you see that a plus b is the same as b plus a using the tip to tail method. So here's a little exercise for you guys to try. Just for the sake of time, maybe we'll jump over it. Or maybe I'll do it together. So we've got this vector here and this vector here. I personally prefer using the longer vector, putting down the longer vector first, but it doesn't really matter because addition is commutative. So vector addition is commutative. So we take this vector, maybe I'll label it just to make it clear. We have A and we have vector B. So we first put down vector A, and then down to the tip of A, we're going to put down the tail of B. And what that's going to do is help us complete this triangle here and give us our resultant vector, which is A plus B. So yeah, that's that. Now, what happens if we need to subtract vectors? Anyone got any ideas? I'll give you maybe 10 seconds to put that down in the Slido. Any ideas on how to subtract vectors? And as I hinted before, we can actually use our addition techniques again. Remember, addition is commutative. And we can actually, it sort of uses something that we didn't talk about too much, but we briefly talked about when we were talking about about unit vectors, how we can multiply things by scalars. We'll look at scalar multiplication in a bit more detail in a second, but I'll give you maybe another 5 seconds to put that in the Slido. How do we subtract vectors? Yeah, so that's about time. So how do we subtract vectors? Well, one method is to draw the opposite vector of the vector being subtracted and then add the two together like normal by using the tip to tail method or the head to tail method. So what I mean by that is if we have vector A and we want to subtract vector B, then we're going to take this vector A, leave it as it is, but what we're going to do to vector B is we're going to flip it. We're going to take it and then we're going to move it in, and then we're going to rotate, we're going to mirror it in the opposite direction. So we're going to make it point downwards like this. It's parallel, right? But it's in the opposite direction. So we have A here and then tip to tail again, because negative B is in the opposite direction. So we just add it like it was some other vector. So we're going to say tip to the tail of negative B, which is going to be downwards. So then the resultant vector is going to start at this point here, end at the head of negative B, so we get A minus B. So very simple, very straightforward. We take vector A, leave it as it is like we did with all the other cases, then we take vector B, but because it's minus, we're going to take negative B, which is the same as B but flipped in the opposite direction, and we're going to add them, and we're going to end up with this vector here. So another method of vector subtraction is to put the two vectors tail to tail. So then, and then drawing a vector from the head of the vector, doing the subtracting to the head of the vector being subtracted from. Now, I don't personally prefer this because it's easy to get confused, and it is sort of counterintuitive. So you want to make sure that you do get it right every time. But yeah, this is another way that you could do it. So you take vector A, and then to subtract vector B, you're going to put A down, and then you're going to go tail to tail, right, for minus B, and then you can complete the vector by going from this end, from that tip of the last vector that you put down, to the tip of the first vector that you put down, and that's going to give you A minus B. Again, it's going to give you the exact same result as what you would have done with the minus B, and then flipping this vector sort of method that we talked about last slide. But this one's maybe a bit more direct, but a bit more likely to be sort of incorrectly done. So just be careful with this one. Oops. Yep, there we go. So yeah, like I mentioned, as we can see, both methods work and give us the same result. So if you have vector A and then we add to it negative b, which is the same as doing minus b, we get this purple vector here, a minus b. And similarly, using the sort of tail to tail method where you put down a and then you put b tail to tail, and then you complete the triangle, it gives you the same exact same a minus b vector. Now remember, like we mentioned, it doesn't matter where this vector starts and finishes, and all that matters is the magnitude and the direction. So although maybe it looks like it's lower down here, and if you did it on the coordinate system, maybe it is lower down for this one here, it actually doesn't matter because all that matters is the magnitude and the direction. So what I mean by that, and it's something important to be clarified, is that if we have our coordinate system, let me just pull up one note quickly. If we have a coordinate system, and we have this original vector here, maybe this time I'm going to call it different. I'm going to call it u with a little bar underneath it to show that it's vector. That u vector is the exact same as this u vector here, right? It doesn't really matter where this vector starts and finishes. All that matters is the length and the direction, the magnitude and the direction. So as long as the length and the magnitude, as long as the length and the direction are the same, they are considered exact same vectors. So yeah, that's why both of these methods give us the exact same result. Okay. So on a piece of paper, try subtracting these two vectors together. What resultant vector do you get by subtracting these two vectors together? Now it might be a bit tricky to put it in through Slido, so maybe I'll do it together quickly. So we have this vector here down this way. So again, method 1 means we take this vector u, we take this vector v, and we make this new vector minus v look pretty much the same as v, but this time same length, but in the opposite direction. So like this, and then we use our tip to tail method. So we take vector u, we put it down, and then this is our new vector that we made, vector minus v, and then completing the triangle, we get u minus v. So that's the first method that we talked about, doing the minus technique. This is the second method that we talked about, so we've got to make sure which one's which. So this one's u, this one's v, and we put them tail to tail, and we finish off the triangle by going from this end to this end. So again, be careful which one you start at, which one you finish at, but as you can see, this red vector here is the exact same as this blue vector here, and therefore you have u minus v here as well. So yeah, those two give us identical results, so which is u minus v, but you just have to be careful with each method because each one has its own tricks. But I personally recommend method 1 because it's a bit more clear and a bit more consistent with your regular addition. So an interesting thing to note is that vectors a plus b and a minus b are the diagonals of the parallelogram created by the vectors a and b. So if we have vector a here, we have vector b here, this green vector in here is a plus b. Because we start at a, go tip to tail with b, and we have a plus b here, right? And it's the same as if we put a and b here, right? And that, by parallelogram law it's called, will give us the same vector. And similarly with a minus b, which is this purple vector in here, using this rule, I guess you could say, that we talked about before, is vector a, and then we subtract vector b, so you put that tail to tail, and then we start at this top, and we finish down this bottom here, so that's going to give us a minus b. So it actually gives us the diagonals of a parallelogram. So if we set up a parallelogram with a, and b, b, meaning that they have the same direction, so they're parallel, and they have the same magnitude, so it's a parallelogram, and we set up the diagonals by going a plus b and a minus b, we see that we have all two diagonals of the parallelogram. Here's multiplying by scalars, the thing that we talked about very briefly before. When we multiply a vector by lambda, now usually Greek letters are what we use to denote a scalar, particularly to differentiate with vectors. Now sometimes you might just see it with a regular letter without the little tilde thing. That still means it's a scalar, but just to be very clear, quite often they use Greek letters like lambda or mu, for example, to demonstrate that it's a scalar. Um, Multiplying a vector by a scalar enlarges or sometimes shrinks the magnitude of the vector by a factor of lambda. So what I mean by that is if we have a vector a and we multiply by 2, right, we have the vector 2a, which is in the same direction, but you take this a vector and you stretch it. You stretch it by a factor of 2 so that we have 1a. Let me rub that out. So we have a here, and we have another a here. So that's what it means by 2a. And if we multiply by something that's less than 1, what that does is it takes this a vector and compresses it. So it becomes shorter. So we have half of a, for example, because our entire a might be something like this. A, and half of a will be in the same direction but half the length. Two vectors are parallel if they are scalar multiples of each other. Now that's a very important thing to sort of make sure that it's clear to you, because many proofs which use vectors try to prove if things are parallel or try to use this property. And so being able to show or being able to use this property is very important when it comes to a lot of applications and a lot of proofs and things. So if b equals k times a, where a is a real number, where k is a real number, then b is parallel to a. All that means is if we have this vector a and we scale it up by something or we compress it by something, but we don't change the direction, and we get this vector out b, then it's parallel. Because clearly, if we haven't changed the direction, all we've done is change the size, it doesn't become unparallel, I guess you could say. It doesn't change the parallel nature of the two vectors. So if we have vector a and we scale it up by a factor of 2, right? So this would be b, for example, right? Vector a and vector b are parallel because vector b is literally just a but scaled up by a factor of 2. So the direction is the exact same. Similarly, half a, even if you compress it, direction doesn't change, so it's still parallel. In the case of minus a and minus 3 on 2a, although it's in the opposite direction, the sort of slope, I guess you could think of it, is the same, and so it's still considered parallel vectors because you can take this vector a and then multiply it by maybe minus 3 on 2, so you get minus 3 on 2a, so it's still a scalar multiple of the original, although it's just in the opposite direction. So this minus flips the direction, 3 on 2 stretches it by a factor of 1.5. So remember earlier how we talked about how to find the unit vectors of magnitude 1? Well, we use the formula a hat, which is equal to a divided by absolute value of a. And like we said, this is because when we multiply a vector a by the scalar 1 on a, we reduce it by a factor of its own magnitude to become 1. All that means is that we take this vector a, which has an original length magnitude a, and then we divide it by itself. So it's got a length of 1. So if the original length is 3, the vector has a length of 3, we divide that by 3, then we're going to get a length of 1. So then a hat would look something like this, and it's going to have a magnitude of 1. Simple as that. So that's where this formula, like we said before, comes from. I guess you could call it a formula. It's not really. It's just compressing a vector, I guess you could say. Here's an example. These sort of questions are probably one of the ones that turn up, and those are sort of the trickier ones, I guess you could think about them as. So if we have a triangle ABC and we're naming the sides AB as being A, so let's label that A, and vector AC as being C. P and Q are the midpoints of AB and AC respectively, so to note that, what I'm going to do is put in lines like this to show that they're midpoints, that they're equal. Part 1 says show that PQ equals half of BC by expressing PQ and BC in terms of A and C. Now, many times these sort of questions try and use these properties of vectors, try and use these convenient notations, convenient notions in order to complete proofs. So we want to show that PQ. So what is PQ? PQ is a vector from P to Q. So that's this one here, equals half of BC. Now what's BC? Well, that's this third side here. So we want to show that this vector PQ between the two midpoints is half of this vector. So it's just taking this vector, scaling it or compressing it down to half its size, and that should hopefully fit exactly between P and Q. So yeah, that's what we want to try and show. How do we approach these sort of questions? Well, first thing to do is try and express BC and PQ. So first, I think it's probably easier to express BC because we don't have to deal with the midpoint thing. So maybe I'll pull up OneNote and I'll show you what I mean by that. So can I copy this triangle over? Well, let me. Okay, maybe it won't. That's okay. We have the vector BC being this one here. So vector BC, to have that vector, we need to start at B, go to A, and then go to C. So vector BC, vector down a bit maybe. Vector BC, we start at B, and we go to vector A, BA, and we add to it vector AC, because we need to go from BA and then down from A to C. Now, AC already has a name. AC is vector C, as they've called it. Oh, vector BA, it doesn't quite have a name yet directly, but we can actually use one of these names that we have. Now, what's special about AB and BA? Well, AB is literally just BA, but in reverse. So we can say that AB is equal to negative BA. So negative AB equals to positive BA, or BA equals to negative AB. Either way works. So from B to A is going to be negative of this vector here, negative of A to B. So we go negative A plus vector AC, so vector C. So we can say that vector BC equals to C minus A. So this is sort of a common approach with many of these questions. If you want to show that something's equal to something, you start with the left-hand side. You start with the left-hand side or the right-hand side, manipulate it and try and express it in terms of whatever they've given you, and then you want to try and do the same to the opposite side and try and show that they're equal. So we've done one side now. Well, we've done half of one side now. So BC, and then we want to halve it, and we want to show that's equal to PQ. What do we do with PQ? Well, PQ is just this vector here. So to get vector PQ, right, we can express that as PA. So that's from there to there, plus vector AQ, so plus A to Q. Now, although these don't have like a very defined name that they've given us in the beginning, we can actually use the fact that it's a midpoint. Well, what does a midpoint mean? It just means it's half the length. So A to P is half the length. So we can all we can do is we take this AB vector and we can scale it down by a factor of 1/2, and that's going to give us this vector AP. So PA, or negative half of AB, because if I pull out the slides, AB, halving that is going to give us AP, but because we want PA, we're going to take the negative of that. So we're going to get negative A. So we're going to take the vector A on 2 to get the midpoint, and we're going to take the negative, so we're going the opposite direction, and then we're going to add to it vector AQ. Now AC already has a name, which is C, so vector AQ is just half of that. So we can say that's equal to vector C, but this time divided by 2 to show that we're talking about the midpoints. So that's equal to C on 2 minus A on 2, so that's 1/2. If we pull out a factor of 1/2, now we can do that with vectors. We can actually treat a lot of these sort of vector manipulations as very similar to algebra. It comes with practice to see where you can do that, where you can't do it. But particularly with dot products, as you would see, it's very similar to sort of expanding multiplication, expanding brackets and that sort of thing. And much of the addition and subtraction is very similar to the algebraic manipulation of just regular algebraic variables. So you have half of c minus a, and you go and you look at that and say, well, I've seen this c minus a somewhere. Well, that was way back here at bc. So half of, we can actually replace the c minus a as bc. So we've proven that pq equals half bc. And this is a very similar pattern for many of these proof sort of questions, where you want to try and express both sides in terms of whatever they've given you and try and show that they're equal. So now we've proven that PQ equals half of BC as they required from the question. Now, what geometric property of a triangle does this express, or does this show? Now, there are a couple of ways to express it, but I guess you could say that the midpoint, or like the side formed by connecting the midpoints of two sides of a triangle, is half the size and parallel to the third side of the original triangle. It really doesn't matter as long as it's clear and you express it in words, it's fine. But yeah, as long as it's a valid statement. Okay, so here's part 3. We want to show that AI equals 1/3 of 2a plus c. This uses a very important sort of concept when it comes to vectors, and that's the subdivision of these vectors. Similar to how we talked about midpoints, we can actually break these vectors down at any point. So now let R be a point on BC, so R is some point on BC, such that RC equals 2 times BR. So what does that mean? We take this BR, right, and we can actually fit 2 of those between R and C. So 2 of BR's fits into RC. So what does that mean in terms of like a fraction? You could think of that as saying this is 1, right? This is 1 piece, and this is 2 pieces. So we can take 2 of these BR pieces and fit them into this RC piece. So what does that mean in terms of scale multiplication or expressing these vectors as scalars? We can actually say that, before we jump to that, let's first express AR. So we want to express vector AR. What does vector AR look like? It's this one here. Connects from vector A to vector R. So that's vector AR here. And how do we express that in terms of B, C, A, that sort of thing? Well, we've got AB, and then we're going to add BR. So we start from A, go to B, and then from B to R. So we can express that as vector AR as being equal to vector AB plus vector BR. So, yeah, AB plus BR. Now, AB already has a name. That one was vector A, if you recall from the previous part. But vector BR doesn't really have a well-defined name yet. Turns out we can actually express it in terms of A and C. And the way we can do that is by relying on our definition of BC. And many times it does actually use previous parts when it comes to these sort of proof questions. So keep an eye on your previous derivations, I guess you could call them. Sorry. Have a look at your previous derivations, and your previous derivations would have shown that BC can be expressed as C minus A. So let's express BR as being, now if this is 1 piece and this is 2 pieces, then that's going to be 1/3 of BC. So 1/3 of BC, like we explained with the splitting that vector into 3 pieces. So we take vector A, and we add the 1/3 BC, which we named C minus A, right? Just from the previous part. C minus A. And so we're going to get A plus C over 3 minus A over 3. So we get A minus A over 3, which is 2/3 of A. And then we're going to get 1/3 of C. So if we pull out a factor of 1/3, we're going to be left with 2A plus C. So we've proven, if we go back up here, vector AR, when we express it in terms of A and C, is equal to 1/3 of 2A plus C. Simple as that. Make sure it's clear. Make sure that it's clear. Make sure that you understand how we got each of those parts, particularly with the splitting this vector up into pieces. But again, if this is your first time seeing it, don't stress too much, because you guys will be seeing it again. Again, practice also does really help. So try and find a few questions from your textbook if you can, or from past papers, and give those a go. Those clarify things. But in general, this is sort of the approach when it comes to vector proofs. Using these using these vector notions and these sort of principles from vectors to prove things, particularly geometrically. Now, remember how I said earlier that vectors can be represented in a variety of ways? So far, we've been looking at directed line segments. Vectors can also be represented as a pair of components. And calculation-wise, it becomes a lot easier when we describe them as a pair of components. So using our knowledge of vector addition, so let's just say we have vector A on a Cartesian plane like so, right? So it starts at the origin, ends somewhere up here. Now, it doesn't really matter where it starts, where it ends. All that matters is the length and the direction. But let's just say it does start the origin in this case. Using vector addition, we can express this vector as a sum of these two. So we go from tail to tip here, and then tip to tail here. So if we call this A, so from our classic example, or maybe we'll rename it, we'll call this U, we'll call this V. So then U plus V equals A. So we can actually use vectors that are perfectly parallel to the x-axis, perfectly parallel to the y-axis. Now, I'm going to temporarily use U and V here, but we're going to change notation up very soon. But maybe I'll actually figure out how long this is. So we have a length of 3 here, so 1, 2, 3 blocks this way. And we have 1, 2, 3, 4, 1, 2, 3, 4, 5 blocks this way. Right? 1, 2, 3, 4, 5. Yeah, 5 blocks this way. So this vector A is composed of 3 blocks to the right and 5 blocks up. Very similar to how we deal with coordinates. So what I'm going to do is I'm going to name 2 basis vectors, they're called. They're going to be of length 1, and they're going to be called I and J. So I is going to have a length of 1, and J is also going to have a length of 1. I is going to be parallel to the x-axis, or horizontal, and J is going to be parallel to the y-axis and perfectly vertical. Yeah? And what that's going to help us do is express any vector in 2 dimensions in terms of I and J. And this is the convention that we use. So just let it load for a second, yeah? So we can actually express I being along the x-axis of length 1. So just to clarify, what's written in words, I has a length of 1, and J also has a length of 1. So they both have equal length, but they're perpendicular to each other. So I is along the horizontal axis, J is along the vertical axis. So what that helps us to do is express this A vector as a sum of two of these basis vectors, I guess you could say. It's called a linear combination. It is a technical term, and we can actually do linear combinations with like infinitely many dimensions if you wanted to. But in 2 dimensions, we can express A as 3i and 5j. So the way that's written is A, and we usually write the I vector first, or the I component first, is equal to 3i plus 5j. So that means 3 of these unit vectors in the horizontal direction, so 1, 2, 3, and then 5 of the vertical unit vectors, so 1, 2, 3, 4, 5, so 3 and 5, and so we have this vector A. That's how you define a vector A, that's how you define a vector using components. So in this case, like I said, A equals 3i plus 5j. Simple as that, 3 across, 5 up, I is 1 across, and j is 1 up. So 3 across, 5 up means 3i plus 5j. Now a vector in the form A equals xi plus yj is said to be in component form because it's being expressed as a pair of components, and any vector can be written in terms of these 2 components, any 2-dimensional vector. So in terms of x and y. The vector A equals xi plus yj can also be represented as an ordered pair or a coordinate sort of thing because it's very similar. So you can write it as xy, but the more common notation that you would see, particularly with operations with this, so when you want to add them and subtract them and things, you'd see this sort of notation here. So you would see curly bracket x, curly bracket close y, xy, and then curly bracket open and close, Or you might see the square ones, which is less common. It's more common for matrices and things, which is sort of further from this, but it's still it's still used by certain authors. But the curly ones are probably the most commonly used ones. So in this particular case, a equals 3i plus 5j can be expressed as 3, 5 like a coordinate, or 3, 5 vertically like this. Now remember, a position vector is a vector. Okay, so remember that we talked about vectors having, like, it doesn't really matter where the vector starts from, but a special class of vectors are called position vectors, and those have their tail at the origin. It's just a sort of definition sort of thing. It's not too common. It's not something that turns up too common, like examining the definition, but sometimes it turns up in applications. So if you have a coordinate system like this, excuse me for that, for the messy coordinate system, but if we have something like this is a position vector, but something like this is called a displacement vector. It is not a position vector. Why does the name position vector come into place? Because it gives you the position of, say, if this is a ship or something, it gives you the position of that ship relative to the origin. That's all. That's pretty much it. So, yeah, as I mentioned earlier, vectors will be equal as long as you have them have the same magnitude and direction. It doesn't matter where you move them. All of them represent vector A. So if this is vector A, all of these ones represent vector A because they all go across by 3 and up by 5. So the only difference here is that, or like the only sort of distinguishing factor here is that this red one is called a position vector because it starts at the origin. But it's not something that's too heavily fussed. Yeah. Now, I'll give you maybe 15 seconds to have a look at this question here. And it asks us to find the coordinates which represents this vector. Put that down in the slido below. Let's see what you guys get. Try using your I and J notation, or you can use the coordinate notation. I just prefer the I and J notation because it's a lot clearer. It stops confusion with the whole coordinate thing. But yeah, either one's fine. I think that should be about good. So how do we find the actual, how do we find the coordinates of this vector? How do we represent this vector in components? Well, first you look at the position vector. So vector AB, the typo there should be OA, sorry. So yeah, so vector AB can be expressed as the difference of the two endpoint position vectors. So what I mean by that is you go finish point, which is B, OB, minus the start point, which is OA. So if we wanted to work it out in components, we could write OB as being 4, 9, and we'll go into a bit more detail in terms of like the actual arithmetic with these sort of things. It's very simple, as you're going to see here. But 4, 9 minus 6, 3 is going to be negative 2, and then 6. But again, even if you didn't want to do that and you have a grid like this, what you can do is you go, well, 1, 2 across, so that means minus 2i. And then you got 1, 2, 3, 4, 5, 6 up, so plus 6j, which is what we have here, which is the same as minus 2, 6. Pretty simple. You just have to go how far across, how far up, and that gives us the vector. So in summary, vector A is OA, which is the same as being expressed in components, xi plus yj, or you can also express it in coordinates, xy, or you can express it as a column vector, xy. Or you can express it in square brackets, which is less common, usually used in more matrix-related things, but you can still use this. You might still see the notation, I guess. So we know how to add and subtract vectors when they are represented as a direct line segment. But what about when they are in component form? How do you add and subtract these things? Well, it turns out, just like the example that we saw before, it's actually very simple to add and subtract in component form. I would argue that it's actually simpler than geometric addition and subtraction. So if we have the addition of two vectors, xi plus y, sorry, x1i plus y1j, and then you add it to x2i plus y2j, what you can do is you can add together the I components, and then you can add together the j components. So that's going to give you your new I component and your new j component. Similarly for subtraction, you subtract the respective components, and that gives you your final output vector. And with multiplication by scalars, you've got lambda times I plus yj. So you've got lambda times the first component, so lambda times the I component plus lambda times the j component. So if you scale a vector, it scales the x component and it scales the y component. It's pretty much all it's saying. Yeah. So this is how it looks like in column vector form, which is even clearer, I think. You just addition, you add the top ones, and you add the bottom ones, and that gives you your new vector. Similarly for subtraction, you add the top one, sorry, you subtract the top ones, subtract the bottom ones, gives you a new vector. For multiplication, it's like a bit like distributing brackets, where you distribute to the first one, distribute to the second one, that gives you your new vector. So let's see how addition and subtraction of vector and components form interacts with the directed line segments. So that's the more geometric way that we talked about before. So if we have a equals minus I plus 4j and b equals 6i plus 2j, their position vectors would look like this on the diagram. So minus I plus 4j means minus 1 across and 4 up. So those are the position vectors, remember, so that means it starts at the origin. So 4j means it goes up. And then vector b is 6i plus 2j, so 6 across, 1, 2, 3, 4, 5, 6, and 2 up, so 2j. And a plus b would therefore be in component form. If we do it just component wise, you got minus 1 plus 6, so minus 1 plus 6 is 5, so 5i. And then you got, for the j's, you got 4 plus 2, so 6j. How does that relate to our geometric interpretation? Well, if we take our vector a and we leave vector a and then we move vector b up so that it's tip to tail, and it looks something like this. And the next slide has a bit more detailed drawing. So we move the vector b upwards. Turns out that the resultant vector that we get is the exact same, and it should be the exact same because we're talking about the same thing. So we have 1, 2, 3, 4, 5, 5 across, 5i, and then we've got 1, 2, 3, 4, 5, 6 up, 6j. And that's that. 5i plus 6j. Now, what about subtraction? You guys have a go at this. Maybe I'll give you, it shouldn't really take that long, maybe 10 seconds to have a think about this. You've got a equals minus I plus 4j, b equals 6i plus 2j. You're asked to find what a minus b is in component form. Again, the geometric form should give you the exact same answer, but clearly you would rather add two numbers than have to deal with cosine rule and sine rule and deal with this geometrically. So yeah, you guys can have a go at that. Give you maybe 10 seconds to do this. Okay. That should be more than enough time. So if you want to do this in component form, you're going to have a being minus 1, 4. And then we're going to subtract b, which is 6, 2. So if you're subtracting components, it's going to be minus 1 minus 6, which is going to be minus 7, and 4 minus 2, which is, 4 minus 2, which is 2. Yeah, okay. So looking at this geometrically, you've got minus 1, 4 here for a, and again 6, 2 here for b. Remember what we do with subtraction, you start at the second one. So if it's a minus b, with not using the first method, using the second method. Now the first method would still work, but here, just for clarity's sake, I'm going with the second method because it's going to make the diagram a lot cleaner. So we've got a minus b, and so we're going to get this vector here. So this final vector, the tip of this final vector to the tip of the original vector. So you've got a minus b looks something like this. And if we're interested in what the actual vector in itself is, then we're going to count how far across. So 1, 2, 3, 4, 5, 6, 7. So minus 7i, and then 1, 2 up, so plus 2j, which if we go back to the original here, it's the same. Minus 7, 2 is the same as minus 7i plus 2j, or we could write it as minus 7, 2. Simple as that. So yeah, doesn't really matter whether you write it in this form or this form, but as long as you do your arithmetic properly, you're going to get the same answer, which is all talking about the geometric form of addition and subtraction. It's unlikely that you're going to have to, there are a few questions that use the geometric notation, the geometric sort of, you set up the vectors and you use your cosine rule, you use your sine rule to find the lengths of these vectors, particularly with like things like a ship heading on a certain heading, and you've got a headwind or a tailwind, or for an aircraft or something. But in most cases, you're going to be dealing with just components, and you're going to be adding components, subtracting components, and scale multiplication of components. So yeah, this is the same vector, but this time it's put in the position vector form, so minus 7 across 2, 1. Okay, so how can we find the magnitude of vector in component form? If we were just dealing with just straight arrows, we would just find the length of this vector. But if we were given it in component form, how do we find its length? Well, it's actually not too hard, because we can split this into 90-degree components. We can go xi and yj. And because we can go xi and yj, which is 90 degrees to each other, we can use Pythagoras theorem. So what is the length of xi? Well, if I has a unit length, or is a unit vector and has a length of 1, then xi has a length of x. So the magnitude of xi is by definition x. Using the fact that it's a unit vector is x. And then yj, the length of that one is y. So if we have a 90-degree triangle with the base being x and the other side being y, what's the magnitude of a? How do we find the magnitude of a? Well, it's not too difficult, because we can just use Pythagoras theorem. So the magnitude of a is just going to be x squared, square root of x squared plus y squared, or if we use it if we write it with a being squared, it's going to be a squared equals to the bottom squared, so x squared, plus the other side squared, so plus y squared. So yeah, just straight using Pythagoras theorem gives us the magnitude of this vector. Additionally, we can use trigonometry to find the angle, which is a vector, the angle with which a vector is making with the horizontal. So that's this angle in here, theta. Or if it's negatively oriented, so for example, something like, so if this is our coordinate system, and the vector looks something like that, then it's going to be this angle in here, right? Again, different in terms of the angle, there are different conventions for it. Just be clear which way you're talking about, and for this triangle, make sure you do 180 minus theta, because what you want to find is the angle it makes with the positive x-axis. Sorry, so this entire angle here. So if this angle in here is theta, what we're interested in this is this bigger angle, 180 minus theta. So some people will say the positive x-axis, or if you're dealing with bearings, and with bearings, you might be considering the vertical positive y-axis. Different conventions for different things, but make sure you get your trigonometry right. So best way to do these sort of questions, rather than blindly memorizing the formula, is draw up a diagram, look at what your trigonometry gives you. And this formula isn't magic, it's just noting that tan of the angle theta is y of x, so that must mean that theta equals tan inverse of y of x, assuming it's acute. If it's not acute, then you have to account for the fact that there is maybe 180 minus or 180 plus or whatnot. Just make sure you draw a diagram, and it should make things very clear. Here's how you resolve a vector into components. So if you're given a vector, A, and we resolve it into components, we can resolve it into the x and y components. So this would be your x component, or your I component, I guess you could call it, and your j component. And the way we do that is just by straight trigonometry. I won't spend too much time explaining trigonometry, because it's quite straightforward. I'll give that to you guys to do as a bit of an exercise. So what you can do is note that x equals to absolute value of a cos theta, or the magnitude of a cos theta. So you take this vector a, and you find the component that's horizontal, so that's going to be this one, that's your x component, and then usually it's going to be this one for your y component. So magnitude of a times sine of the angle theta. Just be careful again, draw your diagram, make sure that you're talking about the right directions, because if you have your vector pointing in maybe somewhere like that, then you've got to be careful because you want to make sure that you've got a negative x value and a positive y value, and you're using the right angles. So let's try some questions. If c equals 3i minus 4j, find c unit vector. Find the vector d of magnitude 6 in the direction of c. Find the vector e of magnitude half in the opposite direction of c. Not too difficult, pretty straightforward. So yeah, let's do this. We've got find c with a little hat and a tilde, so that means a unit vector. So first, to find the unit vector, what we need to do is find the magnitude of c. And just before we do any vectors question, I think it's good practice to draw the vector. So we have 3i, which means 3 across in the positive direction, and then 4j, which is downwards by 4. So like this. So that's 3 across that way, 4 down this way. And then so you've got magnitude of c, just by Pythagoras theorem, should give us 3 squared plus 4 squared. So that's 9 plus 16, so 25 or 5. So Pythagorean triad there. 5 is going to be the magnitude of c, so to find the unit vector c hat, let me open up OneNote to give us some more space. So let's see. Yeah. So to find the vector c hat, we're going to take this original vector 3 minus 4, I'm going to write it in component form, and I'm going to multiply it by 1 over the length, so dividing it by the length, so 1 over 5. So you can leave it as that, or you can write it as 3 over 5 minus 4 over 5 as being c hat. So that means that the unit vector c is 3/5 minus 4/5. Easy as that. That's the unit vector. That's the unit vector in the direction of c. Part 2 says find the vector d of magnitude 6 in the direction of c. So to find that vector, what we're going to do is we're going to take this original vector c, and we're going to find the unit vector, which is what we've done here, and we're going to multiply it by a factor of 6 because it takes that unit vector, stretches it by a factor of 6, so it gives us a magnitude 6 in the same direction as c. So all it takes is so vector d is going to be given by 6 times the unit vector in the direction of c that we found. So 6 times 3/5 minus 4/5, so that's going to be 18/5 and minus 24/5 in the j direction. So yeah, if we write that in component form, it's going to be 18 over 5i minus 24 over 5j. Pretty straightforward. For part 3, it says find the vector e of magnitude 1/2. Now that's not too hard because it's pretty much the same as part 2, but this time instead of 6, it's 1/2. But what do we do for the opposite direction? Well, to find the vector in the opposite direction, all we have to do is put a negative sign in front of it. Because remember how when we were subtracting vectors, we just put a negative sign in front of it and that flipped the direction? Same thing works here. What we're going to do is we're going to take this e vector, and we're going to make it by taking this original c hat vector. We're going to multiply by 1/2 to make it half the length. So it's a unit vector and we scale it down by 1/2, so it's half the length. And we're going to take minus. Right? So minus is going to flip it, so we're going to get minus 1/2 of 3/5 comma minus 4/5. Sorry, 3/5 4/5. So if we have that, that's going to give us minus 3 over 10 and 8. Sorry, and 4 over 10. So it's going to be minus 3 over 10 and 2/5. Not too difficult, pretty straightforward. Yeah. Okay. So that's the I and J components, and those are 3 parts of that question. That's a fairly straightforward question. It's unlikely that you're going to get something as easy as that, but it's good to practice these easier ones and then jump into some of the hard ones. Make sure that you've got the content down. How are we doing for time? Okay, so maybe I'll do these two, and then if we have time, I'll come back to the quadrilateral one. But this one's not too difficult. It's again component form sort of thing. So we're gonna get a minus b. So minus 1320 minus b, which is 215. So that's a minus b, by the way. What does that give us in terms of components? Well, we've got minus 13 minus 2, right? So that's going to be minus 15. And we've got 20 minus 15, so that's going to be 5. So if we've got that, so if we've got that, that gives us the a minus b vector, and we want to find the magnitude of that. So that's going to be the Pythagoras form of that, I guess you could say. And if we draw it, it's going to be negative 15 across this way, and then 5 down this way, so it's going to look something like that. So 15, negative 15 this way, 5 this way, so it's going to be negative 15 squared, which is going to be the same as 15 squared plus 5 squared, so 250, square root 250, and that we can split into 25 and root 10, so that's going to be 5 root 10. Yeah, easy as that. So the magnitude of a minus b is 5 root 10, because we first component-wise find a minus b, and we find the magnitude. Next question is a bit more interesting. It says find the value of k, so the vector ka plus 2b is parallel to the x-axis. So let's find a general expression for ka plus 2b. Ka plus 2b. Let's deal with it component-wise. Let's rewrite the components out. Ka plus 2b is going to be 2 times 215. So we get minus 13k, because when we expand out the k, we get minus 13k and we get 20k, just by property of scale multiplication, plus 4, plus 30. Right? That's going to be our ka plus 2b vector. And if we want it to be parallel to the x-axis, that just means that we're going to have some scalar multiple of 1, 0. And why do I say 1, 0? Well, that's because that's going to be our I vector. I vector is always perfectly parallel to the x-axis, so any scalar multiple of it is going to be perfectly parallel to the x-axis. So this mu just means some scalar multiple of this 1, 0 vector. So if we take the y, so in these sort of situations, we've got two equations. We've got minus 13k plus 4 equals mu times 1, or just mu. And then the second equation is 20k plus 30 equals mu times 0, which is 0. So I think it's easier to deal with the second equation. Now, both equations should be consistent for this to work out, but it's easier to deal with the second equation. Sorry, it's easier to deal with the second equation just because we don't have to deal with mu. So then we can conclude that 20k plus 30 equals to 0. And so that's going to say that 20k equals to minus 30. And so we get k equals to minus 30 over 20. So we get minus 3 on 2. So the value of k of minus 3 on 2, make sure that ka plus 2b is parallel to the x-axis. And to make sure that this equation is consistent, all you have to do is, or to find out what the value of mu is, all you have to do is sub in k equals minus 3 on 2 back into the original equation here, and that will give you the value of mu. But that's not what we're concerned about here. We've figured out that a value of minus 3 on 2 makes the vector ka plus 2b parallel to the x-axis. Yeah. So in terms of quadrilaterals, maybe we'll jump over it for now, and then if we have time, we'll come back to it. Okay. Now time for some calculus. Remember, Maths Extension 1 is an extension of Maths Advanced, so many of the topics in MX1 course build on the topics you'd learn from the Maths Advanced course. So yeah, being familiar with the Maths Advanced course is very important for the Extension 1 course, and don't neglect Maths Advanced, because a good chunk of Extension 1 is built upon Maths Advanced. So a key part of the Maths Extension 1 course is the Advanced course. So as much as I enjoy teaching you MX1 integration techniques, like integration by substitution or finding volume of solid revolutions and things like that, I can't really do that until we talk a bit more about math advanced integration. But what we can still do is that related to MX1 integration. So part of the calculus topic in MX1 syllabus requires you to be able to integrate expressions that lead to inverse trig functions and integrate sine squared x and cos squared x. So we're actually narrowing down this calculus syllabus just because you guys need to talk a bit more about the advanced calculus part in order to do some more of the MX1 specific calculus, particularly application sort of questions. So what I'm going to do is talk about things that are related to the MX1 integration topic. Yeah. So integration and differentiation are opposite operations, and I'm sure you would have heard the term integration before. Quite often, you would have also talked about things like antiderivatives, and it's quite closely related, or you could even think of them as the same thing: integrals and antiderivatives. Although they talk about fundamentally different things, and it's very interesting why they're related. Because one thing you're talking about rates of change, and other thing we're talking about like area. Why should they be related? That's interesting, and that's something called a fundamental theorem of calculus, which is a bit beyond the scope of the course. But if you're interested, feel free to investigate. So yeah, if we know how to differentiate inverse trig functions, we can actually go the other way to get inverse trig results by integrating. So because we're relying on the fact that dy dx, that differentiation is the opposite of integration. So if we see something that we know is a result of differentiation, we can actually use that to figure out what the original is. So that's going to be integration. And I'll talk about what that means in a second. So in the year 11 course, you learned about differential calculus and how to find derivative of an equation. And the syllabus stop point in the course is find derivatives of inverse functions by using the relationship dy dx equals 1 over dx dy. We need either directly use that relationship or use the chain rule. They're actually quite related. This is pretty much an effect of the chain rule, but we can use that to figure out certain integrals which might not be that easy at first glance. So from Maths Advanced, you should have also learned that d by dx of sine x is cos x, and d by dx of cos x equals negative sine x, and we'll be using that properties in just a second. So because we know how to deal with those things, and we have that specific syllabus stop point, we can actually use that to differentiate inverse trig functions. So in terms of, before we jump into some calculus, let's look at some inverse trig functions. So things like sine inverse x, cos inverse x, tan inverse x, or you might see it as arcsine, arccos, and arctan. But we want to try and differentiate these things. How do we differentiate it? That's the question that we want to deal with here. Well, to do that, we can actually use these properties of like inverse trig functions alongside the properties of calculus. So what I mean by that is, I'll do one example. I'll do sine inverse x, and cos and tan is very similar. Well, particularly cos is very similar. So I'll do sine inverse x, and hopefully that should clarify things, and you should give cos inverse x a go on your own, or you can look it up. It's, again, these sort of derivations aren't something that you expect to do each time you use them. It's just good to be familiar with, and it's a good technique to be familiar with, although it's very unlikely that you'll be asked to reproduce something like this in the exam situation. So let's say we define an equation, y equals sine inverse of x. If we take the sine of both sides, we end up with sine of y equals to x. Now, I'm not going to be too careful with like boundaries and limits, as in domains and ranges of these functions. That's something for you to think about, and that's actually a very important part of this. But just because this is sort of a crash course thing, I don't want to spend too much time thinking about it. It's not too difficult. We just have to remember that sine inverse of x is trapped between a certain domain and a certain range, and we have to account for that whenever we're doing these sort of things. But yeah, we've got sine y equals x. Now I'm going to do something interesting. I'm going to take the derivative of both sides. So I'm going to say d dx of sine y equals d dx of x. Now, if we take the derivative of both sides, what do we end up with? Well, we end up with, on the right-hand side, it's pretty straightforward. What do we get when we take the derivative of x? It's just going to be 1. So on the right-hand side, we're just left with 1. On the left-hand side, we actually have to use the chain rule. And the reason for that is because this sine y is not in terms of just x. It's in terms of y. So we're going to have to use the chain rule. And it's very similar to what you would have seen in related rates, where you take the derivative of something that, so you take the derivative with respect to something that's not directly in the equation, but still related to it. So what you have to do is multiply by dy dx in this case, and then you multiply that by the derivative of the function itself, so cos y. And if you're curious about where this came from, it's literally what you would have done before in your related rates questions. It's a product of the chain rule. So it is a consequence of the chain rule. So dy dx equals dy dx cos y equals 1. And so if we rearrange this, we get dy dx equals 1 over cos y. Right? And interestingly enough for us, we can actually express this cos y in terms of x. And we want to express it in terms of x. So to do that, what we're going to use is the Pythagorean identity. So if you guys think back to your trig identities, the most famous one, or the most commonly used one that you would have seen, is sine squared y plus cos squared y equals 1, or it's called the Pythagorean identity. And so then we end up with cos squared y, if we rearrange for it, is going to be equal to 1 minus sine squared y. And so if we square root both sides, we get cos y equals square root 1 minus sine squared y. And we have to be careful with positive and negative signs here. For now, I'm going to say it's always positive, and just believe me for now. But I think if you go back and have a think carefully, you should be able to see why it is always positive. And so we get an expression for cos y in terms of sine y. But where have we seen sine y before? We saw sine y here expressed as just equal to x. So we can actually replace this sine squared y with the square root of 1 minus x squared. So we've actually gone ahead and expressed cos y in terms of x only. So cos y equals to the square root of 1 minus x squared. And so dy dx equals to 1 over the square root of 1 minus x squared. And so we're done. That's how you find the derivative of sine inverse of x. The derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Now that's a known result. That's not something that you have to derive each time, but just know this is how you would get to it. You have to use the chain rule, you have to use a Pythagorean identity, and you end up with this result. And you can use a very similar approach to find that for cos inverse of y. Just give it a second to load. Yeah. So, these are your results. So d by dx of sine inverse of x is 1 over square root of 1 minus x squared, like we showed. D by dx of cos inverse of x is the same, but with a negative sign. And d by dx of tan inverse x is 1 over 1 plus x squared. These results, I believe, are on your formula sheet, so they're not something that you have to memorize. And the derivation is not something that you have to be able to reproduce, but just know that that is the way that they're derived, and that is a possible technique. Now that we know that, we can go the other way and integrate those values to get some of our standard integrals. Because we know that when we integrate, it's the opposite of differentiating, and differentiating is the opposite of integrating. So if we find that we're asked to, so we're not given this sine inverse of x, cos inverse of x thing, we're just given this 1 over the square root of 1 minus x squared thing, and we're asked to integrate it. Well, we know what's the function that we get when we try and what's the function that we get when we differentiate sine inverse of x? Well, it's 1 over square root of 1 minus x squared. So the integral of that has to be equal to the sine inverse of x. So we can go the other way. And we can actually generalize it for not just 1. Now, it's not too hard to get from here to here, but I won't focus too much on the details. It's just a matter of factoring out like a factor of square root of a. Factoring out a factor of a squared from the inside the square root, but again, not too hard there. Okay, So moving on, in the Year 12 3-unit course, you'll need to know how to integrate sine squared x and cos squared x. But how do we do it? Now the answer lies in the cosine double angle formula. So let me show you how you would approach this. Okay. So if we have cos 2 theta, that's not too hard to integrate. We know how to integrate cos theta, which is just going to be sine theta. So cos 2 theta, when we integrate it, is going to be 1/2 sine 2 theta. Not too difficult. So what we're interested in is how can we integrate something that looks like cos squared theta or sine squared theta? The answer to that is try and turn it in terms of this thing. Now, how do we relate these two quantities? Well, that's by using our cosine double angle formula. So if we use the double angle formula for cosine, it's cos 2 theta equals cos squared theta minus sine squared theta, just from your trig identities. And so that's going to give us, so that's going to show that, let's say we want to integrate cos squared theta, we're going to say cos 2 theta equals cos squared theta. First time we're going to leave as it is. Because we want everything in terms of just cos squared theta, what I'm going to do is use the Pythagorean identity to express sine squared theta in terms of cos squared theta. So Pythagorean identity says sine squared theta plus cos squared theta equals 1. So we end up with 1 minus, so we end up with sine squared theta. If we want to express it in just cos squared, in terms of just cos squared theta, it's equal to 1 minus cos squared theta. So we get cos squared theta minus 1 minus cos squared theta. Like that. And so we get cos squared theta minus 1 plus cos squared theta. And we end up with cos 2 theta as being 2 cos squared theta minus 1. And because we want cos squared theta on its own, we're going to move everything across except for the cos squared theta. So we get 2 cos squared theta equals to cos 2 theta plus 1. And then I'm going to divide through by 2. So we're going to end up with cos squared theta equals to 1/2 cos 2 theta plus 1. And there we have it. We've expressed cos squared theta in terms of cos 2 theta and 1. Now, 1 is just a constant, so that's not too hard to integrate. And cos 2 theta, again, isn't too hard to integrate because we know that when we differentiate 1/2 sine 2 theta, we end up with cos 2 theta. So we know that the integral of cos 2 theta is 1/2 sine 2 theta. Okay. Yeah, it's all good, I think. So then, in this case, if we want to integrate cos squared theta, we can make our lives so much easier by expressing it in terms of what we showed before, 1/2 cos 2 theta plus 1 and d theta. Half cos 2 theta is just going to be that. And then I'm going to leave it as plus 1/2 here. Now, usually, or like sometimes you can pull out the half in front, but the reason I'm leaving it in here is because actually, it might be helpful for us to pull it out. I will pull out the half before we move on. So if we pull out the factor of 1/2, we end up with integral of cos 2 theta plus 1 d theta. And so we end up with 1/2. The integral of cos 2 theta, as we showed up here, is 1/2 sine 2 theta. plus the integral of 1 is just going to be theta. So it's going to be integral of cos squared theta using our identities, which we expressed in terms of cos 2 theta, is equal to 1/4 sine 2 theta plus theta on 2. And so we're done. That's how you would integrate cos squared theta. Now, I know that seems like a sort of roundabout, longish way to deal with this sort of thing, but it turns out this formula is actually on your formula sheet to express cos squared theta in terms of cos 2 theta, but it's good to be familiar with how to approach or how to get that formula. Yeah, and in the old syllabus, it wasn't actually on the formula sheet, so it's something that you have to derive each time. So I think it's a pretty valuable skill to be able to do. Okay. Here's sine squared x. I already showed cos squared x. Sine squared x is fairly similar, so maybe save some time. I won't go through that one. But yeah, I think that's all we have for today. We do have a bit of time left, so maybe I'll jump back to the quadrilateral example. And that we should have enough time to do this one as well, and that should be it for today. So we'll jump to this quadrilateral vectors example, and that we'll call it day for today. So the quadrilateral ABCD has vertices A, B, C, and D. Show that AD equals BC, and hence explain why ABCD is a parallelogram. Now, just a big tip before we jump into this question. Know your quadrilaterals, know your properties of quadrilaterals. What is a rhombus? What's a parallelogram? How do you define squares, rectangles? It seems a bit obvious, but what happens with diagonals, that sort of thing, because that it can sometimes be part of the question, or sometimes can give you hints in terms of what you need to do and how you need to approach these questions. But for this specific question, we got quadrilateral ABCD has vertices A, B, C, and D, and show that AD equals BC, and hence explain why ABCD is a parallelogram. So we got ABCD. Now, I won't yet draw it, and the reason I won't yet draw it is because we don't know which way the labels go. But if we can show that AD equals BC, then we should have a fairly good idea of what the parallelogram looks like. But in this case, I don't know which way it goes, so I'm just going to deal with it in algebraic component form. It's not the best practice in 2 dimensions, but sometimes it's sort of the necessary thing that you have to do. So AD, how do we express AD? Well, it's the vector from A to D. And remember, each of these points have their own position vectors. So it's it's the finish minus the start. That's something that you guys can use all the time. If you've got the vector AD, that's going to be OD minus OA. Now, what is OD? OD is that coordinate vector that we have here, minus 5, 6. What is OA? That's that other coordinate vector that they've given us, 7 minus 5. So then if we subtract those two, we get minus 5 plus 7, which is going to be 2. And we get 6 plus 5, which is 11. Now the next vector that we're asked to show is BC. So let's see what we get when we find vector BC. Same approach. Finish, OC, minus start, so minus OB. So we get OC is 10, 9. Minus OB is 8 minus 2. And so we get 10 minus 8 is 2. 9 plus 2 is 11. So you get AD equals to BC. And so we've shown that AD equals BC, and so we've shown that these two vectors, AD and BC, are equivalent. So we've shown AD. Now I sort of have a rough idea of what the parallelogram looks like. Vector AD and vector BC. Looks like that. They're two equivalent vectors, right? So what happens if we close off these two here? We have vector AB, and we have vector ADC. If we can show that these two vectors are also equivalent, then it's a parallelogram, right? Now, there is a couple of ways of approaching this. You can use the parallelogram law of addition to show that it's a parallelogram, but I think it's easier to show that AB and DC are the same because it's pretty much the same process, just with different numbers. If you show that they're the same, we've shown that they're equal in length and they're parallel. So we've got two pairs of parallel sides So we've shown that these two are parallel and are of equal length. If we can show that the other two sides are equal length and parallel, then we're done. Then we've shown that it's a parallelogram, just by properties of parallelograms. So let's show that AB, let's see what AB gives us first. Vector AB is OB minus OA, which is the end minus the start. And you can double check that by using your vector subtraction sort of laws, the geometric approach. It should give you the exact same thing. So OB is 8 minus 2, minus OA is minus 7 minus 5. So 8 plus 7 is 15. Minus 2 plus 5 is 3. So 15, 3. And what does vector DC give us? Vector DC is OC minus OD. Well, that's going to be OC is 10, 9. Vector OD is minus 5, 6. So we end up with 10 plus 5, so 15. 9 minus 6 is 3. So we've shown that AB is equal to DC. So therefore, we've shown that, coming back to our diagram, these two vectors are parallel. They're also of equal length. So we've concluded that because they're equal, just by definition of vectors, if two vectors are equal, they have the same magnitude and direction. Vector AD, or we can talk about magnitudes first maybe. Magnitude of AD equals to the magnitude of BC, and AD is parallel to BC. We've also shown that AB is the same length as DC, or CD, either however way you want to put it, and vector AB is parallel to DC, not the magnitude, sorry. AB is parallel to DC, like this, and so we've shown that we've got two pairs of sides which are equal length and parallel, and therefore it must be a parallelogram. And that's that. We've proven that it's a parallelogram. Hope I spelled that right. It looks right, I think. But that's it for that question. Any questions, put them in the Slido, but I think that's all the time that we have today. We have another 10 minutes-ish, so feel free to put in questions, sort of Q&A time, whether it's about the content or in general about Maths Extension 1. Feel free to ask, and I will try my best to get back to you. But yeah, that's all for today. Thank you, and see you guys next time, potentially.